Hello and welcome. Today we're going to be doing an example of finding eigenvectors and values of a 3x3 matrix. I'm going to start with this matrix here. We're just going to do one example in this video, short and sweet. Okay, we're going to start with this matrix 2, 0, 0, 2, negative 2, negative 1, negative 2, 6, 3. So there's our matrix. Okay. So we know that we need to find the three lambda 1, lambda 2, and lambda 3 eigenvalues of this matrix. And we're going to do it by solving the characteristic equation, which is the determinant of A minus lambda I, which is going to be equal to 2 minus lambda, negative 2 minus lambda, and 3 minus lambda. Those are all in the diagonals. We have a negative 1 there. 0 is on that part up there. And all that just stays the same from the regular matrix. Okay. So now we're going to have to take our determinant. We're going to start by using that value there. We're going to have 2 minus lambda. Okay. And then we have to take the determinant of all of this right there. Then we have a negative 2 minus lambda times 3 minus lambda, all times, and then we got to subtract negative 6 from it, so that negative 6 times another negative becomes a positive 6, like that, okay? And notice here that the next two things in the top row there are both zeros, so that means that this is going to be our characteristic equation. So now we just have to multiply this out to see what we get here. Okay. So let's multiply that out. We can do a few things here, though, to simplify our work. First thing, I'm going to multiply the whole equation. Because it's equal to 0 here, I'm going to multiply the equation by negative 1. Get a lambda minus 2 there. Same thing inside of here. I can multiply, well, we'll factor out a negative here and then get a 2 plus lambda, okay? And then finally, I'll factor out another negative 1 to get lambda minus 3, and that will take care of that negative there. And then we have a plus 6. Okay. So that is our matrix so far, or that's our characteristic equation so far. And that's equal to 0. Okay. So now we just have to multiply it all in. We have lambda plus 2 times a lambda minus 2 times a lambda minus 3 plus 6 lambda minus 2, all equal to 0. Okay, so it's going to take a little bit to multiply all this out. Let's start by multiplying out this right here. That's going to give us a lambda squared minus lambda, and then a plus 6, okay? And that's going to be times lambda minus 2. And that's also going to be a plus 6 in there. I can factor out the lambda minus 2, and then we're going to get a lambda minus 2 times lambda squared minus lambda plus 12. Okay. From here, we're going to set that equal to 0. Let's see, what are we going to do now? It looks like, oh, I'm sorry. I have a little error there. I see the error now. What we have here, this should have been a minus 1 there, in which case we have a plus 0 there. Okay, so that's better. And now we have a, sorry, I have to, okay. We can factor out the lambda. Like that, and that's equal to 0. Just to tidy up things a bit, I'll make that a lambda minus 1 there, and that's equal to 0. They're all equal to 0, so I can just change the sign of this thing at will. All right, so now we have our roots. We have lambda 1 is equal to 0. Lambda 2 is going to be equal to 2, and lambda 3 will be equal to 1. Okay, so there's our roots. The next thing we can do now is find v1, which is going to be associated with lambda 1 is equal to 0. Okay, so for this, it's going to be fairly straightforward that we're going to solve a minus lambda 1 I times v1 is equal to the 0 vector, which reduces to a very simple just a times v1 equals 0. Okay, so we can solve this one with row operations. So my v1 in this case is going to be, we have to put the unknowns in as just an a, b, c. Like that. Clearly a is going to be 0 straight away. And we can see that because if we look at the top row of this matrix, there's only one way that that equation is going to equal 0, and that's if a is equal to 0. Okay, so that simplifies my problem quite a bit, and now I just have to worry about b and c. So we have a negative 2, negative 1, 6, 3 is equal to b times c, or b and c in that vector there is equal to 0, 0. If we examine this carefully, we see that if we look at the rows here, we see that basically call 1 is just 2 times call 1 is equal to call 2 for both top and bottom rows there. So that suggests the following. If we can say that b is equal to 1 and c then is equal to negative 2. And that should yield the correct result. So putting all this together, we're going to get v1 is equal to 0, 1, negative 2. So remember that the eigenvector is not unique. Any scalar multiple of this eigenvector would also work. Okay, so we could multiply this by 2, and that would also be an eigenvector. We could multiply it by negative 3. The only thing we don't want to multiply it by is 0, because then we would lose all the information about the vector that's there. Okay, so, and this is associated with lambda 1 is equal to 0. So we found our first eigenpair. Now I'm going to find some new space to do our work again. And we're going to go to lambda 2, which is equal to 2, and try out that. We're going to try to find v2 now, figure out what that is. So a minus 2i multiplied by v2. And we're going to say v2, again, is equal to a, b, and c, are unknowns that we're going to use. And that's going to be equal to the 0 vector. And this resulting matrix here is going to be 0, 0, 0 after we subtract the 2, and then 2 minus 4, negative 1, -2, 6, and then 1. A, B, C, like that. Okay. And that is going to be equal to 0, 0, 0. All right, so we want to know what the solution to this equation is. We already don't have one of our rows. What I can see here, though, is I want to do some row operations, but if I take row 1 and I add it to row 2 and make that my new row 2, that should help me out in understanding how to solve this one. All right, and that's going to yield to me 2, -4, -1, and that's going to be a 0 there, and that's going to be a 2 there, and that's going to be a 0 there. And again, that top row doesn't matter. A, B, C. Now I can solve this equation a little bit easier. And clearly, the bottom row there shows me that B has to be equal to 0. This is the only way that bottom row is satisfied. Okay? So by knowing that, then I can explore the second row here and see if I can find a way to solve that. And that looks pretty straightforward. We know B is 0. So really I just have a 2A minus C is equal to 0. Another way to say that is 2A is equal to C. All right? So remember, eigenvectors are not unique. There's infinitely many of them. They're all scalar multiples of each other. So all I have to do is find A, and C that satisfy this equation. What I'm going to try then, of course, is A is equal to 1, and C, of course, naturally is going to equal 2. So putting all that together, I'm going to get V2 is equal to 1, 0, because that's what B is, and then C is equal to 2. There we go. And that eigenvector is associated with 2, the eigenvector, or the eigenvalue, equal to 2. All right, pretty good. I think now we have just one more piece of work to do. We're looking at the eigenvalue now of lambda 3 is equal to 1. So again, we want to find V3 now. We don't know what it is, A, B, C. Okay, so let's go ahead and do that. Our A minus 1 times I multiplied by V3 is going to be equal to 0. And that equation is then, if I write out the matrix explicitly, it's going to be 1, 0, 0, 2, -3, -1, and then -2, 6, and then 2. We have an A, B, and C. All right, so I need to solve this linear system. Straight away, I can see the top row gives us one solution for one of our values already. We know that A has to be equal to 0. Okay? All right, so we've seen this sort of thing before in the previous one. In the previous lambda 1 case. So all of a sudden now our problem got a lot simpler. Now we have a -3. It's really just that lower submatrix then that has all of our information in it to solve BC. Okay. Again, note here that that column 1 times 3. Column. Pardon me. Column 1 is equal to 3 times column 2, right? And that's true for both the top row and the bottom row, all right? So that means, of course, that I can take B equals 1 and C equals 3, but then I'll make it a c equals -3, and then I should have it. So put that together, we get v3 is equal to 0, 1, and -3. All right, and that's going to be associated with lambda 3 is equal to 1. Right, so putting it all together, we found all of our eigen pairs. And in fact, I have them all on the screen here. I'll circle them for you guys. Right there. All right, well, I hope you found this informative. Just a quick little problem where we solve for all the eigenvectors. It's fairly repetitive. You're going to do it. Once you find that characteristic equation, there's those 3 different linear systems you have to solve. It's kind of a chore, but it works out just nicely. Thank you very much.